Okay, this video is on the unit circle. Now, we've already talked about how the measure of an angle in radians is equal to the arc length divided by the radius. In other words, if I'm looking at this angle right here, we call this angle theta, then the measure of this angle in radians is equal to this arc length divided by the radius of this circle. Well, if the radius of this circle happens to be equal to 1, by the way, that's what a unit circle means. It means a circle that has a radius of 1. If the radius of my circle happens to be equal to 1, notice what happens to this equation. If this radius is equal to 1, let's say if radius equals 1, then the measure of my angle in radians becomes arc length divided by 1, or the measure of the angle in radians is equal to the arc length. So now, if I want to know what is the measure of this angle right here, if I just know what the length of that arc is, that's going to be equal to the measure of that angle in radians. Well, what if I wanted to talk about this angle where we go all the way around the circle? In other words, the entire circumference of the circle. We already know that's 360 degrees. And we also know that the circumference of a circle is equal to 2 pi times the radius. So that's the length, if you want to think of that as the arc length of the entire circle, that's 2 pi times r. Well, if the radius of my circle happens to be equal to 1, then this circumference is equal to 2 pi times 1, which is 2 pi. In other words, and since I know that this circumference is equal to 2 pi, that's that arc length, the length of this arc all the way around the circle, well, since my radius is equal to 1, that arc length is also equal to the angle in radians all the way around the circle. In other words, the measure of an angle, if I want to call this one rotation around the circle, the measure of this angle all the way around the circle is equal to 2 pi radians. For a unit circle, remember the measure of the angle is equal to the arc length. I know the arc length, if the radius is equal to 1, the arc length is 2 pi. Therefore, the measure of the angle in radians for one full rotation around the circle is equal to that arc length, which is 2 pi. Angle equals arc length. Well, if the measure of an angle of one rotation around the circle is equal to 2 pi radians, in fact, let's go ahead and write this in. Let's say if I'm starting right here at this point, and this is 0 radians, and I go one full rotation around the circle and come back to here, and that is an angle of 2 pi radians, which is approximately equal to, if I multiply that out, 2 times 3.14, that gives me approximately 6.28 radians. So if that's the measure of an angle that's one full rotation, what would be the measure of 1/2 of a rotation around the unit circle? 1/2 of a rotation would take me over to here. Well, half of that rotation, half of a rotation around the circle would be 1/2 of a full rotation. A full rotation is 2 pi. So if I just say 2 pi times 1/2, because I'm not going all the way around, I'm just going half of the way, then that would be equal to 2 pi times 1/2 is just going to be equal to pi. So a half a rotation around my unit circle is going to be equal to pi radians, which is approximately 3.14 if I write it in decimal form. Well, what about the measure of an angle that is, let's say, 1/4 of a rotation? Well, 1/4 of a rotation, that would take me up to right here. 1/4 of a rotation, I would want 1/4 of the measure of a full rotation, so 2 pi times 1/4, and that's going to give me 2 pi over 4, which is pi over 2 radians. So the measure of an angle formed by a fourth of a rotation is going to be pi over 2, which is approximately, if I punch this into my calculator, I get a decimal value of 1.57 radians. And what about if I go, let's say, 3/4 of a rotation? I start here, I go 3/4 of a rotation, so 3/4 of a rotation. That's going to be 3/4 of a full rotation, so 2 pi times 3/4, and that's going to be, let's see, 6 pi over 4, which reduces to 3 pi over 2 radians. So the measure of an angle of a 3/4 rotation is going to be 3 pi over 2, and if I punch that into my calculator to get a decimal number, that's approximately 4.7 radians. So now I know the measure of these 4 different angles, in radians. If I go 1 full rotation around the unit circle, I know that the angular measure is going to be 2 pi radians, or 6.28 radians. If I go a fourth of a rotation, I've got pi over 2 radians, 1.57 radians. If I go a half a rotation, that's pi, or 3.14 radians. If I go 3/4 of the way, that's 3 pi over 2, or 4.7 radians. So let's take a look at how we can use this in these problems here in examples 1 and 2. Example number 1 says, what angle in radians corresponds to the given number of rotations around the unit circle? So, in other words, I'm being asked now in example number 1, if I make a rotation around the unit circle, 1 rotation, how many radians is that angle going to be? Well, 1 rotation, we just looked at that, it's going to be 2 pi times 1 rotation, which is 2 pi radians. So I start here, I go all the way around, that's 2 pi radians. How many radians would be 1.5 rotations? So if I go 1 time around and then another half, that's going to put me over here. How many radians would that be? Well, that's going to be 2 pi times 1.5. 2 pi times 1.5 is 3 pi radians. So I go 1.5, that'd be 1 time around is 2 pi, and then another half is another pi radians, that's 3 pi radians. How many radians corresponds to a negative half a rotation around the circle? So if I start here and I go in a negative direction, 1/2 of a rotation, looks like that should be negative pi radians. So let's see, 2 pi times negative 0.5, and yeah, that gives me negative pi radians. Okay, here's one with kind of an odd number. What would be the angle measure in radians corresponding to 4.27 rotations around the unit circle? So 4.27 rotations, if I start here and I go 4.27 rotations, let's see, that would be 1 rotation, 2, 3, 4 rotations, and another 0.27 rotations is a little more than a fourth. That would put me about right here. And what would be the angle measure for 4.27 rotations? Well, 2 pi times 4.27 equals 8.54 pi radians. So I can see all I need to do to find out the angle measure for some number of rotations around the unit circle is just multiply those number of rotations times 2 pi. Now, take a look at example number 2. Example number 2 says, give the quadrant corresponding to the angles with the following measures. When it says quadrant, it's referring to the quadrants of the unit circle here, the quadrants of the xy axes. This is quadrant number 1, quadrant number 2, quadrant number 3, and quadrant number 4. So remember, if we start here at the kind of 0 point, and if we make some number of rotations around the unit circle, then we're going to end up with an angle in one of these quadrants. If I just go a little bit around the unit circle, like say to right here, my angle is going to be in quadrant 1. If I go, like say, almost a half a rotation, my angle is going to end up over here in quadrant 2. Well, if I go more than 1 rotation, though, then I'm going to end up somewhere either in quadrant 1, quadrant 2, quadrant 3, quadrant 4. I don't know where my angle is going to end up. Well, let's see if we can figure that out. Give the quadrant corresponding to angles with the following measures. 7 radians. So I know that if I go a half a rotation around the circle, that's 3.14 radians. I know if I go a full rotation, that's 6.27 radians. 7 radians must be something greater than 1 full rotation. In fact, it looks like it's going to be somewhere here in quadrant number 1, because if I go 1 full rotation and then another quarter of a rotation, that would put me at 6.28 radians plus 1.57. That would be 7.8 approximately. That'd be too far. So it looks like I'm going to end up in quadrant number 1. And in fact, one way that I can kind of do that calculation is I can say 7 radians. And if I subtract out the 6.28 radians, in other words, if I subtract out 1 full rotation around my unit circle, what I'm left with is 0.72 radians. And since 0.72 radians is between 0 and 1.57 radians, it's greater than 0, and it's less than 1.57 radians, then I know that my final angle must be in quadrant number 1. Let's take a look at this one. What would be the quadrant corresponding to an angle of 8 radians? Well, again, if I go 1 full rotation around the unit circle, that's 6.28 radians, so I know it's more than that. If I go another quarter of a rotation, that's going to put me up to 7.8 something. Well, I'm going to be going farther than that, so I must not be in quadrant 1 anymore. It's looking like I'm going to end up in quadrant 2. So let's do what we did before, which is let's subtract out 1 full rotation, or subtract out 6.28 radians. So 8 minus 6.28 is 1.72 radians. And so I subtract out that 1 full rotation. 1.72 radians, I see that's greater than a fourth of a rotation, but it's less than a half a rotation. So I must be somewhere in quadrant 2, because 1.72 is greater than 1.57, but it's less than 3.14. Therefore, I'm going to be in quadrant 2. All right, example C, 12 radians. All right, once again, if I go all the way around, that's 6.28 radians. If I go all the way around a second time, that's going to be 12.56. It's going to be 12.56, so I don't go quite 2 full rotations, but it looks like I'm going to go almost 2 full rotations, which looks like it would put me in quadrant 4. So let's see if that's right. 12, I subtract out 1 full rotation, which is 6.28, and that gives me 5.72 radians. 5.72 radians is greater than 4.7, but it's less than 6.28. So I know that I went 1 full rotation around, and then I went almost another full rotation. Therefore, I'm in quadrant 4. Okay. Once again, remember that the definition of radian measure is arc length divided by radius. So, and we could also write this as theta equals, let's say, AL over R. R is radius and theta is in radians. Well, if I want to make this into a formula for arc length, it doesn't take too much manipulation here to see that my arc length is going to be equal to theta times radius. And in fact, that is the formula for the arc length of a circle, theta times r. And notice that this angle theta must be in radians. And this is the radius of the circle. Now, you may recall the formula for arc length that you learned in geometry when you were measuring your angles in terms of degrees, And if you do, then you remember that that formula was a lot longer and more complicated. That's one of the advantages in working in radians, is that things involving circles, if you work in radians, the formulas often become a whole lot simpler to use. So here's my formula for arc length of a circle. So let's take a look at example number 3. It says find the arc length corresponding to the given angle in a circle of radius of 5 centimeters. Well, I have my arc length formula here. All I need is the measure of an angle in radians, the radius of a circle, and I should be in business. So example 3a, 2 radians. So arc length is going to be the angle in radians, 2, times the radius of the circle. Well, I'm told the radius of the circle is 5 centimeters, so 2 times 5 centimeters equals 10 centimeters, and that's my arc length. Example B, 5 radians. Arc length is the angle in radians, that's 5 radians, times the radius of the circle, which is 5 centimeters, 25 centimeters. So that's pretty simple. Oh, wait a minute. Now we get to example C, and I'm given an angle measure, but now I'm not given the angle measure in radians. I'm given the angle measure in degrees, and in order to use this arc length formula, my angle measure has to be in radians. So now all of a sudden I've kind of hit a roadblock here. Hopefully that's not too much of a roadblock, and you can figure out how to calculate the arc length of this angle on a circle of 5 centimeters. So I'm going to leave C and D for you to work on, and we will take a look at these tomorrow in class.